Hello everyone to this Living Lab lecture series. My name is Elias Werner and I will talk about big data context awareness by drift detection. First of all, I would like to start with a short motivation and show what we actually mean when talking about big data. In this table you can see different units of measures that you might know from your daily business. For example, we have a byte that has the capacity of 1 letter. We have a kilobyte that can store 1 page of a novel and a megabyte that is enough space for a whole novel. Following this metaphor, a gigabyte could store a shelf full of novels and a terabyte is then in the order of magnitude of a library. In our daily life, we have gigabytes of data on our smartphone and we might have an external storage device where we have space for terabytes of data. Watching 150 hours of 4K content on Netflix is also in the order of magnitude of a terabyte. Anyway, when talking about big data, then we might consider bigger units. Therefore, let's assume that a terabyte is a water drop. Then a petabyte of data would be roughly a small glass of water. To categorize that unit, Facebook generated 4 petabytes of data every day already in 2014. When looking a bit further, considering our metaphor, an exabyte would mean a small aquarium full of water. In the first quarter of 2022, the global mobile network data traffic reached 3 exabytes per day. When talking about zettabyte, the terabyte water drop became now a garden pond. And this amount of data will be created, captured or replicated about 80 times in the year 2022. The next unit in our scope is the yottabyte. That is approximately now a small lake like the Carola Lake in Dresden. It is expected that 1 yottabyte of data will be created, captured or replicated in the year 2030. Following this, the water drop becomes a big lake like the Lake Senftenberg when considering a prontobyte, a data unit of the future. However, with this big amount of data also some challenges arise. Therefore, some V-words exist that categorize several challenges. The 3 most common ones are volume, meaning data at scale and refers to the sheer amount of data. Velocity means data in motion and refers to the high speed of the data generation and how the data needs to be processed. Variety refers to data in many forms, meaning that there are a lot of different types of data available, like text data, multimedia data, structured data, or unstructured data. Moreover, there is a 4th V, that is veracity, referring to data in doubt and considering the change and the uncertainty in the data. Indeed, this is actually the challenge in which the topic of today is categorized mostly. In a few seconds I will explain the meaning of veracity a bit more. Just let me mention there are also more of these V-words describing big data challenges such as value, visualization, variability or virality, and I am sure that more will come since we are just at the beginning of the big data age. Okay, big data, big veracity. The term veracity was introduced as the 4th big data V by Schreck et al. In 2012. It is addressing the uncertainty within the data and managing the reliability and the predictability of imprecise data. One example for that are GPS values. That's recording might be influenced by external factors like skyscrapers that reflect the GPS signal. This might be considered when evaluating the sensor data values. Another example are weather conditions or economic developments that are very complex scenarios with many influencing factors. Moreover, veracity also considers the information value of the data that might change. For example, the number of cyclists in a city per hour depends on the season, the infrastructure, or the daytime, and to assess this number, we need to consider this information as well. Let's introduce a concrete use case. For that, we give the definition of context at first. The context is any information that characterizes the situation of an entity. For example, considering the entity smartphone, the context is the smartphone's brand or fabric, the geolocation or the user who uses the device. Our use case refers to a paper that we have published in 2021, and it aims to recognize a transport mode based on smartphone sensor data in crowdsensing campaigns. So the goal was to predict the transport mode of a smartphone user that sends data to our machine. In general, this scenario can be considered as big data since we have a high amount of data to be processed, we have data in motion, and also the challenge of veracity comes in here due to the different context of a smartphone in a crowdsensing campaign. To make that a bit more clear, what the use case is about. We have a lot of people, that is the crowdsensing part. And all of these people have smartphone devices to collect sensor data. So actually, this last part is the sensing part and the first part is the crowd part. This data is then sent to our artificial intelligence that recognizes the transport mode of the user, and in this case it should predict whether the user is a cyclist, is a pedestrian, uses bus, streetcar, train, airplane, ferry or car. The challenge of veracity is here not only due to the big number of different people in the crowd, but also due to different geolocations like mountains, countryside, like lowlands, city, and so on. And multiple different devices may also introduce here veracity, since there are many users that may use different devices for that sending part. Moreover, there might be some relevant context information like speed limits in different countries or the right-hand traffic versus the left-hand traffic. A quite abstract view on our approach to tackle that challenge of transport mode recognition is given here. At first, we collected data in Dresden, then we trained an artificial intelligence based on that data, and then we predicted the data coming from a crowdsensing campaign. To put it in a nutshell, the results are that it worked well in cases where the context is similar to the training context, and it didn't work well in cases where the context is different. To explain that results a bit more, let's consider a simplified example about that. When training our artificial intelligence, we have a user here with a smartphone that collects sensor data when going by bicycle. This data is then sent to the artificial intelligence and used to teach the AI to predict the transport mode, bicycle, based on that sensor data. Something similar happens when the user goes by foot. Smartphone sensor data is here sent to the AI that learns to predict pedestrian based on that sensor data. Hence, during the training, the AI gets specialized to the context of the smartphone for simplification in this example to the user. In the prediction phase now, it is then easy for the AI to predict the correct transport mode for that known context. The AI can correctly predict when the user goes by bicycle, and the same holds for the pedestrian mode. However, if we consider a different user, it is likely that the AI has problems predicting the correct transport mode and might predict pedestrian even if the user was a cyclist. In this example, it is quite easy to get an idea about the problem. Let's assume that the AI learned to predict the transport modes based on the velocity profile of user 1. That might be a sporty person. Then it could be that another person, for example an elderly person, might have a velocity profile as a cyclist that is closer to the pedestrian profile of the younger person than to the cyclist profile. Since the AI does not know the context of the data to predict, it might classify the cyclist as a pedestrian. So the question that arises from that is how to deal with a different context. In the training phase, we might have only limited knowledge about the context in the prediction phase. And what if we are not aware of relevant context information? We may not know the relevant context information in the training phase already. One approach to deal with that questions is concept drift detection. The definition of a concept according to Webb et al. Is as follows. At a time t, with a given random variable x over vectors of input features and a random variable y over the output classes, a concept refers to the joint probability distribution over x and y at time t. Concept drift then means that the joint probability distribution over x and y has changed at a time t plus 1. So, in our case, the sensor data is the x and means accelerometer, magnetometer, gyroscope and GPS, and the y is the transport mode, meaning bicycle, feet, bus, car, train, streetcar and plane. When considering now only the GPS speed values for only the bicycle transport mode, but for two different users, we see that these values vary between these two users and that the joint probability distribution over x and y might have changed, meaning that the concept drifts from user A to user B. So, is it likely that concept drift occurred in our use case? Yes, it is very likely. And why? Well, since my grandma rides a bicycle differently than I do. Yeah, this is actually a quite intuitive explanation, but let's make that a bit more concrete and map that again to our crowdsensing scenario. So as we already know, the context of the entity smartphone affects the collected sensor data values. In the training phase now, the AI learns how to behave based on the context of the training data and represents a certain concept. For the crowdsensing use case, it means that we consider some people, devices and geolocations in the training phase. However, this is only a proportion of the context in the prediction phase due to the nature of crowdsensing. We do not only have a lot more different users, but also devices and geolocations. This then also means that it is quite likely that concept drift occurs. Luckily, in the literature there are some methods available to deal with concept drift. In general, there are two categories: supervised methods and unsupervised methods. The supervised ones require data labels and rely on the observation whether the probability distribution over x and y has changed over time. For the unsupervised case, no data labels need to be available, since these methods might consider the output y prime of an artificial intelligence for some given input x. Then they observe whether the probability distribution of x, meaning only the input, has changed or over x and y prime. Considering this, our example can be enhanced by such a concept drift detection method. For the first user now, this does not really make a difference here. The method detects there is no drift and the AI predicts the correct transport mode as usual. For the second user now, the drift detection method may detect a drift and incorporate this information by some drift handling, which supports our AI then to predict the correct transport mode, also for this user. Now, the question is how to handle a detected drift. And here I just mentioned three approaches, but in general there is a big variety in concept drift handling considering different use cases, base classifiers and data types. The first example here was introduced by Mustafa et al. In 2017. It is an unsupervised drift detection method observing the probability distribution over the input values. It uses then an ensemble of classifiers for predictions and adapts to concept drift by updating this ensemble and it supports also novel class detection. In the same year, Xi et al. Introduced a method relying on a supervised drift detection. They are also using an ensemble of classifiers for the predictions. If a drift is detected, they apply transfer learning techniques to adapt the ensemble to the new concept. In the year 2021, Greco et al. Introduced a method for concept drift detection that uses predicted labels of a pre-trained classifier. They observe then the joint probability distribution over the input and the predicted labels. However, they mention the adaptation of concept drift as a future work. And that highlights that there are still open questions how to deal with that problem adequately. Besides that, it is also worth to point out that the most of the studies for concept drift detection and handling focus a lot on the correctness of the approaches. There is a lack of studies considering big data requirements, especially concerning the volume and the velocity, so the runtime requirements for drift detection. And therefore we have to ask, is concept drift detection and concept drift handling ready for the big data age? To assess it, we are currently about to benchmark, so to measure the state-of-the-art concept drift detection methods from a performance point of view, and we focus especially on the unsupervised case. Moreover, we plan to investigate the performance of the implementations. For such investigations, the performance analysis community supports us with tools like ScoreP, a measurement infrastructure to record performance events, and the tool Vampire, a tool for visualization and to display recorded performance data. If you are interested in that topic, feel free to watch our Living Lab lecture series about big data performance analysis. Okay, so these are here the references that I have used for this lecture, and yeah, that's it. Thank you very much for listening.